The next talk is entitled A Comparison of Height-Integrated Ionospheric Currents and Magnetic Perturbation in the Auroral Zone by Asgeir Brekke.
I'll talk about some current calculations we have been doing up in the Auroral zone from data taken by the Chattanooga radar. And there is probably no other instrument that have been used so extensively in the study of ionospheric physics, except perhaps from ionozones, as magnetograms or magnetometers. But there is probably no other instrument that has been so much misused in the same field either. As we all know, the magnetometer responds to several different effects, such as ring currents, ionospheric currents, induction currents in the Earth, and probably several other sources. And the final result, which is a variation in the Earth's magnetic field, represents therefore an integral of many processes. From the ionospheric point of view, it is therefore important to exclude all non-ionospheric sources in order to understand anything about ionospheric processes causing magnetic field variations. Proper estimates of such non-ionospheric sources is not easy to do, and how much more difficult is it not then to infer from magnetograms any processes in the magnetosphere. We will therefore find that in order to learn about Magnetosphere-Ionosphere Coupling, we cannot start with a magnetogram on the ground and work ourselves up in altitude, but rather start at the top and work down, if that was possible. Fortunately, it is now possible, in the auroral zone at least, to work oneself down from the ionosphere, and thanks to the results we have obtained at the Chattanooga radar. As explained earlier by Dupnik and Banks, we are able to measure a height-averaged neutral wind in the E region, in addition to the electrostatic field perpendicular to the magnetic field, and also in addition to height-integrated conductivities. Therefore, it is a rather straightforward task to derive estimates of ionospheric currents perpendicular to the Earth's magnetic field. Such estimates have obviously been done previously by several workers, but there has never been, to my knowledge, possible to measure ionospheric currents over such long time periods as it is now possible at Chattanooga. And I would like to show you the first slide. This is a slide or an experiment made during a very quiet day in Chattanooga. This is the electric field, it's the northward and the eastward components. Midnight is about 10 UT, and we see here just before midnight an increasement in the northward electric field. The eastward component is rather small all the day. The conductivities have a nice sinusoidal variation and presumably are due to solar zenith angle variation. So it's the ionization from solar EUV radiation. There's a little peak at night time corresponding to this enhancement of the field. Down here we have plotted the electric field, if we would say, corresponding to the neutral wind we are measuring in the ionosphere. And we can see that for some of the periods, especially in the daytime, the electric field, or the induced electric field, if we will say, from the neutral wind, is relatively large compared to the electrostatic field, presumably mapped down from the magnetosphere. And it is even opposite directed to the electric field at some periods. So here we are back to the dynamo theory again. I will now show you the other slide where we make a comparison between the currents we calculate from the first data I showed you and compare the currents we get with the magnetogram at college, which is about 40 kilometers away from our radar. The H component agrees fairly well, but there are some disagreements between the D component and the northward current we calculate. This was a very quiet day, so nothing much is gained here probably. There was no current and there is no magnetic field fluctuations. There is an interesting disagreement here though, even though the scale probably in this figure tends to exaggerate the discrepancy. there is a discrepancy between our northward current in the ionosphere and the D component you see on the ground. And we see that this is especially true during daytime, and therefore this disagreement probably has some relevance to SQ current system in the auroral zone and polar cap area. I'll now show you another day which Peter Banks showed you previously. And the first experiment we did was with 3 positions, antenna in 3 different positions, and in order to get the ion velocities and so on, we had to make the time resolution was about 30 minutes. Here it's now done by moving the antenna around in a circle, so we get a time resolution of 6 minutes, and the results tend to be much more noisy, but it isn't that much noise. It's in fact real fluctuations. And we can see that there is a tendency for the conductivities to increase when, in general, the electric field turns from north to south in this period. And as Peter pointed out, there are some interesting positive or northward components in the electric field here, enhancement in the component, which corresponds to positive base in the magnetogram. And in fact, if you look at magnetograms from Ionospheric in north, which is far in the north of Alaska, to Sitka in the south, we will see that these positive bays occur simultaneously all along the meridian or all over the chain we are looking at. So these are, if we will call it, intensifications of the auroral oval or expansion of it. There is an interesting feature here. The conductivity suddenly disappears. And this occurs just in a period where there is a westward electric field. And I want you to remember about this time. It's about 8, is it? About 7 hours, I think, UT. And here we have plotted the currents again and compared them with the magnetogram fluctuation at college. We see that all those positive bays, they fit very well until this one. I said that all these were simultaneous in Alaska, but this one seems to occur at different time in the different station when you look from south in Ionospheric from north in Ionospheric to south in Sitka. So there are obviously some structures, local enhancement in the current. So we estimate a current that's too large compared to the magnetic fluctuation here. In the negative base, we see a fairly good correspondence, but some of the peaks do not fit as well as others. And this was the time where the conductivity disappeared. And we see that the northward component was fairly strong, or the H component was fairly positive and suddenly disappeared. And we can see that this hole, if we will call it, moves southward from Ionospheric to south of College in about 1 hour. Oh, I have to be quick here. Here's another day. We have very large electric fields, and very northward in the beginning, then turns westward for a while, and then southward. And when this field is westward, we have a big increase in the conductivities, directly opposite to the day we saw before. And we look at the currents here. You see we have fairly good correspondence between the H and the northward component, but there are disagreements in the D component and the eastward component of the current and the H component, but there are disagreements between the D and the north component of the current, which we think in these periods are related to parallel currents. There are a lot of precipitation going on here, and we have made simultaneous measurement with the Triad satellite during these periods, and we hope that we can find out something about the influence of parallel currents here. I jump quickly over another one. This is the day that Bauer showed similar measurements down in France with the radar there. And here is the enhancement of the conductivity I was talking about happening just where his increase in the westward flow was seen down in Saint-Quentin. There is a related phenomena to this, and that is magnetic micropulsation, which have been used extensively to study the source in the magnetosphere causing these kind of fluctuations. And it's thought that it is Alfvén waves coming down from the magnetosphere down to the ionosphere. it's a sudden commencement happening just here, and we see a strong switch in the electric field occurring just when there is an enhancement of the conductivity. After the commencement, there is an oscillation in the electric field, which is a typical PC5 oscillation. Time resolution here is now 30 seconds. If we think that this electric field is related to the wave coming down from the magnetosphere to the ionosphere, we should expect that the polarization of this field should correspond very well to the polarization in the magnetic field. And I have made a plot of these two things, and we see that there's a circularly polarized electric field, there's an elliptically polarized magnetic field in this period. And this polarization pattern tends to reverse somewhere in here, while this is more steady. So there are disagreements between these two, which probably can be explained by induction in the Earth and many other sources. But when we compare the current we calculate during these fluctuations, we see that the H component and the current in the eastward plane are in fairly good agreement, but the D component and the northward current are in disagreement, more or less. And this shows some of the complications we have when we try to find the polarization pattern in the magnetic field variations. Thank you.
Could you explain briefly the method you use to distinguish magnetospheric electric fields from those driven by neutral winds?
Well, I should probably not say that it is magnetospheric electric fields, but it is electric fields measured in the F region in the ionosphere. So they are obviously of magnetic origin, but how they are related I won't dare to tell because of the mapping problem. But the field we are measuring in 250, 300 kilometers, we assume is an electrostatic field which is related to the magnetospheric electric field.
And the neutral wind one is just measured lower down?
The neutral wind is measured, we derive the neutral wind because of the difference we see in the ion velocities in the F region and the ion velocities we see in the E region.